In this video, we're going to discuss combustion analysis. So combustion analysis is a common method for determining the percent composition and empirical formula of an unknown organic compound. And organic compounds are compounds that are composed of carbon and hydrogen atoms. And they may also contain oxygen, nitrogen, sulfur, or some other nonmetal atom. Here's a few examples of some chemical formulas for a few organic compounds. So for combustion analysis, the organic compound that we're analyzing is burned or combusted with excess oxygen. A combustion reaction produces carbon dioxide and water. So assuming complete combustion, we should get all of our all of our reactant converted into carbon dioxide and water. The carbon dioxide and water are then separated on a gas chromatograph and quantified. Here's a kind of a schematic of a combustion analyzer. We take our organic compound that we're analyzing, put it in our combustion chamber, and combust it or ignite it with oxygen, excess oxygen, and we produce water and carbon dioxide. The water and carbon dioxide are collected in special chambers, which can then be analyzed, and we can figure out the mass of water and carbon dioxide produced. Here's a general chemical formula for a combustion analysis reaction. We have our hydrocarbon, our organic compound. This one only contains carbon and hydrogen. You could also have one that contains oxygen or sulfur, as we mentioned before. It's reacted with excess oxygen, and all of our sample is converted into carbon dioxide and water. The key to understanding combustion reactions is this. The moles or mass of the carbon and hydrogen that are produced. So the mass of this carbon and the mass of this hydrogen that's produced is equal to the mass of the carbon and the mass of the hydrogen that we started with in our original sample. There's no other source of carbon or hydrogen. There is a extra source of oxygen, so that's a little trickier if your compound contains oxygen. But we know, if we know the mass or moles of carbon and hydrogen that are produced, we know the mass and moles of carbon and hydrogen that we started with. That's the key to understand this. So be sure you take a minute to be sure you appreciate that fact. The overall schematic or scheme that we might want to use to solve a combustion analysis problem is first we want to get the initial sample weight. We then want to combust it and figure out the mass of the carbon dioxide and water that's produced. Now this is probably given in the problem that you're solving. And then we convert these into moles, but not moles of carbon dioxide, moles of carbon and moles of hydrogen. We then take the ratio of carbon to hydrogen, and we can use that to figure out our empirical formula. So let's try a problem. Take a look at this problem. In this problem, you're given a sample that contains only carbon and hydrogen. So we don't have to worry about oxygen or nitrogen or anything. Read this question carefully and see if you can determine the empirical formula first, and then the molecular formula for this organic compound. Pause the video and give it a try. Okay, so the first step I would do is to, let's determine the moles of carbon that were in the carbon dioxide and the moles of hydrogen that were in our water that we produced. We're given the mass of carbon dioxide and water that we started with. I convert the moles of the grams of carbon dioxide to moles using the molar mass. For every 1 mole of carbon dioxide, it contains 1 mole of carbon. So I figure out the moles of carbon that are produced. Same thing with water. I convert the grams of water to moles using the molar mass. For every 1 mole of water, it contains 2 moles of hydrogen, H2O. So that's an important ratio. Don't forget that step. So I've calculated the moles of hydrogen that were produced. And remember, the moles of carbon and hydrogen that are produced were equal to the moles of carbon and hydrogen that you started with. That's the key. So the second step, we just need to determine the molar ratio of carbon and hydrogen in our empirical formula. So I take the whichever moles is the smallest, I take that and divide both of the moles by that. So I take the 0.8 moles of carbon and divide it by 0.8. And then the 2 moles of hydrogen, I divide that by the 0.8. And I get a ratio. For every 1 mole of carbon, my sample contains 2.4 moles of hydrogen. Now again, for an empirical formula, we have to have the simplest whole number ratio. So to get that, I could multiply by 2, 3, or 4, but those don't give me whole number ratios, so I have to multiply by 5. If I multiply by 5, I get C5H12. So my empirical formula is C5H12. That's the empirical formula for my unknown compound. So for step 3, we can now determine our molecular formula. We know our empirical formula, and we can determine the molar mass of the empirical formula, C5H12, and the molar mass of the molecular formula, the molecular compound, we are given that in the problem. So we just take the ratio of those and we get a factor of 3. So we have to multiply our coefficients, or our subscripts rather, by 3 to get the actual molecular formula. So C15H36 would be the molecular formula of our compound. Let's take a look at one other problem. This problem is going to be a little bit trickier because this problem contains carbon, hydrogen, and our initial compound contains also oxygen. So take a minute, pause the video, and see if you can solve this problem. I'll give you a hint. It starts off the same as the other, but then we have to do a little something different to figure out the moles, the mass and the moles of oxygen. So pause the video, see if you can figure it out, and then I'll work through it with you. Okay, so let's take a look. First thing I want to do is determine the moles of carbon and carbon dioxide produced and the moles of hydrogen in the water that was produced, just like we did before. So I take the mass of carbon dioxide in water and convert them to moles of carbon and moles of hydrogen. And again, don't forget this, 1 mole of water contains 2 moles of hydrogen. Okay, so I know the moles of carbon and hydrogen that we produced. I convert the moles of carbon and hydrogen, I'm going to convert those to grams. You'll see why in just a second. So I take the moles of carbon and use the molar mass to get the mass of carbon, and the moles of hydrogen, I'm going to convert that to grams of hydrogen. So this tells me from my original sample contained 11.5 grams of carbon, and my original sample contained 1.29 grams of hydrogen. That's going to come in play here. We can use that to determine the grams and then the moles of oxygen. I know the mass of my original sample. I know the grams of carbon that my original sample contained and the grams of hydrogen. So if I subtract the sum of these two from the mass of my original sample, the only thing that's left is the oxygen. So I can use calculate the grams of oxygen by subtracting the mass of hydrogen and carbon that I produced. So it would look something like this. I started with 28.1 grams, that was given in my problem. My sample is composed of 11.5 grams of carbon, 1.29 grams of hydrogen. We know the law of conservation of mass tells us we can't create or destroy mass. So if we subtract these two from our original mass, what's left must be the mass of oxygen. So my sample originally contained 15.3 grams of oxygen. So now it's an easy task to convert my grams of oxygen into moles. So now I know the moles of carbon, moles of hydrogen, and the moles of oxygen in my original sample. Now I just have to figure out the molar ratio to get my empirical formula. So I take the carbon moles, hydrogen moles, and oxygen moles, and I divide them all through by the smallest number. In this case, it's 0.957. And so divide everything by 0.957. I get 1 mole for every 1 mole of carbon. I get 1.3 moles of hydrogen, and my sample contained 1 mole of oxygen. Again, let's figure out the simplest whole number ratio. So we have to multiply all of our subscripts by 3. So we get C3H4O, and that is my empirical formula. Finally, we can figure out our molecular formula. Take the molar mass of our empirical formula, and we divide the molar mass of our molecular formula by that of the empirical formula, and we get some factor 2, which tells me that my molecular formula is twice that of my empirical formula. So we multiply all of our subscripts here by 2 to get the molecular formula, C6H8O6. So review these steps. Be sure you're familiar with the steps and you understand the basic principle behind combustion analysis and how it demonstrates the law of conservation of mass. And be sure you can solve these problems in the future.